In the first part of 6-6, we talked about kites. Now we're going to talk about trapezoids. So what exactly is a trapezoid? A trapezoid is a quadrilateral with exactly one pair of parallel sides. So if we were to draw a trapezoid, it might look like, well, if we have a parallel side, and let's go parallel side here. Notice that these two lines are parallel, and then we're going to have two lines connecting these. And this would be a trapezoid, and as I said, we have two parallel sides. This is a possible trapezoid. What we call this bottom, what we call it both of them, is the parallel sides we call a base. And we call the non-parallel sides, we call these legs. And as you can probably tell just by looking at this, just because these two bases are parallel does not mean that they are congruent. They are not the same length. Trapezoid does not imply they are the same length. Same with the legs. The legs are not necessarily the same length. More notation, we call all of the angles formed at the bases, we call them all base angles. So in this case we have base angle here, and base angle. This is specifically when we're talking about the bottom base, this longer base. These two would be the base angles. And the same would be said for up on top. When we're talking about the top base, we'd be talking about these two are the base angles. Although it doesn't happen all the time, if these legs are congruent, again the non-parallel sides, if those non-parallel sides are congruent, we call it an isosceles trapezoid. And it's simply a trapezoid with congruent legs. We have three theorems dealing specifically with isosceles trapezoids. Our first theorem about isosceles trapezoids is theorem 663. And it says if a quadrilateral is an isosceles trapezoid, then each pair of base angles are congruent. So remember, the base angles are the consecutive angles that share a base. And notice that we do have a trapezoid here. We have just one pair are congruent, and we have, parallel. One pair of sides are parallel, and we have the congruent sides here. So it is isosceles. Now what this theorem tells us is that the base angles, let's say angle A, is going to be congruent to angle D. So we have these two angles are congruent to each other. Furthermore, what we also know is that these two top angles are going to be congruent because they are also base angles. So angle B is congruent to angle C. B and A are not necessarily congruent. Same with B and D, C and D, and C and A. These are not necessarily congruent. It's just the ones that share a side. Our second theorem is almost the exact opposite of 6-6-3. It says if a trapezoid, not necessarily isosceles, if a trapezoid has one pair of congruent base angles, then the trapezoid is isosceles. So if we were given a trapezoid such as trapezoid ABCD here, notice it is a trapezoid because we have the two parallel lines. But the difference here is we are not told that we have congruent sides. We are not told that the legs are congruent. What we are told, though, is that angle D is congruent to angle C. This is different from 6-6-3. Since angle D is congruent to angle C, what we can say is that ABCD is isosceles. And this is directly from this theorem. It's almost the exact opposite of 6-6-3. And our next theorem about isosceles trapezoids says, a trapezoid is isosceles if and only if its diagonals are congruent. Remember what this if and only if means. It means that this statement is a biconditional statement. You can read it both ways, forwards and backwards. So what does that mean? This theorem says two things. If a trapezoid's diagonals are congruent, then it's going to be isosceles. Or if a quadrilateral is an isosceles trapezoid, then its diagonals are congruent. So what you can do is you can determine if a shape is an isosceles trapezoid. That's with this first half. Or you can determine that the diagonals are congruent. That's what the second half of this biconditional statement. All right, let's go ahead and do an example using this stuff. What we're given is this trapezoid here, EFGH, and two parts. Part A is find the measurement of angle F. Find the measurement of this angle up here. Also, what we want to do is find FH. We want to find the length of FH. So let's start with part A. Part A, first thing is first, what I notice is that this is a trapezoid. You have two parallel sides, and that's it. But you also have two congruent sides. You're told it's congruent. So we're told since FE is congruent to GH, this is isosceles. This is more just so we lead into which theorems we can go into. So knowing that it's isosceles, we can use the theorems from before. So if we're trying to get to angle F, trying to get up here, we don't have anything that relates angle F and H. I say H because that's all we know right now. But what we do have is F to G. And I say F to G because these two are base angles with each other. So we know what F is, or we know F and G. We know F and G will be congruent. So let's try to see if we can determine what G is. Well, if FG is parallel to EH, as it is, we know they are parallel, what we can do is use same side interior angles. Well, same side interior angles, let's talk about angle H as we have as 49, and this angle G right here. We know they're same side interior angles because I'm talking about the top line and the bottom line. Are both of our angles, the 49 and the red angle G, are they both inside or outside of these lines? They're inside. Same side or opposite side of our transversal? Same side. So same side interior angles are supplementary. So we know that 49 plus the measurement of angle G is equal to 180. Therefore, by subtracting, we see the measurement of angle G is equal to 131. Since it's 131, and also you know that because this is isosceles, angle F is congruent to angle G, so the measurement of angle F is equal to 131 degrees. And now we are done. Moving on to part B, we need to find the length of FH. So notice we don't have an FH yet. FH would be from F to H here. We don't have that. If it helps, you can draw that in. Just because the line doesn't exist doesn't mean we can't talk about that line. Now, just like last time, we notice that FE is congruent to GH, and so we know that this is an isosceles trapezoid. Obviously, we didn't change anything, so it's still isosceles. So meaning we can use our theorems from before again. These theorems tell us that since this is isosceles, the diagonals are congruent. So meaning this could just be as simple as saying that FH is congruent to EG. And now we know that FH is equal to 25.4 because EG was 25.4. Now we're about finished, but we do have one more theorem, and it deals with the mid-segment of a trapezoid. The mid-segment of a trapezoid is a segment whose endpoints are the midpoints of the legs. And this theorem, it says that the midpoint, or the mid-segment of a trapezoid is parallel to each base, and its length is 1/2 the sum of the lengths of the bases. Now this is actually very similar to the triangle mid-segment theorem, just with a slight difference when we're talking about the sum of the lengths of the bases. So we're going to jump straight into an example here using this theorem because there's not much to it. Now we have this trapezoid again, A, B, C, D, And we have a mid-segment. This is the first time seeing a mid-segment, but XY is the mid-segment here. How do I know it? Well, because we have AD. AD seems to be cut right in half. Means X is a midpoint. Also, BC is also cut in half. So Y is the midpoint. So this line is going through two midpoints of the legs. Alright, so now we need to find, what the idea is to find the length of DC. How can we do that? Well, we're actually going to use this mid-segment theorem immediately. What this mid-segment theorem tells us is, well, since 1, we know XY is a mid-segment. So since we know XY is a mid-segment, 1, we know that XY is parallel to the bases. Okay, that's awesome, but it's not very important right now. And that's because we're dealing with the length of the segments. So dealing with the lengths, just reading our theorem, it says that its length means the length of the mid-segment, meaning the length of XY is equal to 1/2 the sum, meaning we're adding together here the lengths of the bases, meaning we can add together AB plus DC. This is exactly what our theorem tells us. Now I'm going to move up a little bit, and what we know the length of XY. XY is 16.5, so that's going to be equal to 1/2 25, because that's AB, plus DC. We don't know DC, we're actually trying to find DC. So how can we solve this now? At this point, a lot of people want to distribute this 1/2, which is fine. You could do that. An easier way, just get rid of the 1/2 immediately. Multiply both sides by 2, or divide both sides by 1/2. Either way, just get rid of that 1/2. So you can multiply both sides by 2. I know that's not the best way to denote it, but multiply both sides by 2. You now have 33 is equal to 25 plus DC. Where did that 1/2 go? Well, when you multiplied that right side by 2, 1/2 turned into 1. So that was the whole idea of multiplying by 2. Alright, now we just solve, and we do minus 25, minus 25. We see the length of DC is equal to 8. And now we are all finished. And to check that work, you could do 8 plus 25 divided by 2 should give you 16.5. So anyway, that's all I've got today. Hope you understand trapezoids. If not, write it down. Write any questions down. And see you tomorrow.